What is the definition of mixture? Mixture is a combination of two or more pure substances in which each pure substance retains its chemical properties. That means if there is mixture of suppose A, B, C, three substances, then all of these three substances, they will retain their individual chemical property that will not be destroyed after mixture formation. Okay. Now mixture may be two types. One is homogeneous, another one is heterogeneous. Okay. So what is the difference between heterogeneous mixture and homogeneous mixture? From the picture you can get some idea. In heterogeneous mixture, here actually we have two components. Suppose A plus B. Okay. So when it is two component, it is known as binary mixture because there is only two. Mostly in this chapter we will study the binary solution. Okay. So heterogeneous mixture A plus B. Here from this picture we can understand that the concentration of, suppose these green ones are B and the violet ones are A. So the concentration of B is more here and concentration of B is more, A is more towards this side. Okay. That means if we take some part of this mixture from this portion and if we take some portion from this region, then these two, their composition is not same. But if it is homogeneous, from whatever is the portion we take some part from this mixture, it will always have the same number of A or B. So we will see some examples of heterogeneous mixture and also homogeneous mixture. So in heterogeneous mixture there will be multi-phase substances. That means substances can remain in different types of phases and it is also non-uniform. But if it is homogeneous, there will be only single phase. Okay, single phase means suppose A and B we have in the mixture. So if A is liquid, then B also be liquid. Fine. And if A is solid, B will also be solid. That means there is a single phase. But if it is heterogeneous mixture, then there may be multi-phase. Okay. So that is the reason that it is non-uniform composition. So here we have some examples of both the homogeneous mixture as well as heterogeneous mixture. Fine. Now whenever we say solution, the first picture that comes in our mind is sugar solution or salt solution. Fine. That means some solid we are dissolving in some liquid and we are getting solution. But solution does not mean that they are always we have to dissolve some solid in liquid like water. Okay. It may be solid we are dissolving in solid, that is also possible, or we are dissolving some gas in some other gas, that is also possible. So that we will see when we will discuss different types of solution. But before that, what is solution? A solution is a homogeneous mixture. Homogeneous mixture we have already seen the definition of two or more than two substances. So if it is only two substances, it will be binary mixture. Okay. It can exist in any state. That is, solution can exist in any state. Mostly the examples that we see surrounding us, it is of liquid, but that does not mean that solution cannot be solid or gas. It can also be gas or solid. So here the picture that we have, suppose the solute is salt or sugar and solvent is water, then after dissolving the solute in the solvent we are getting solution. Okay. So in solution there is actually two part. One is solute part, another one is solvent part. Fine. Another example of solute and solvent. Now the solvent is liquid and also the solution, the solute, that is also liquid. That means liquid we are adding to another liquid and we are getting solution. So as I have said that solute may be liquid also. It is not necessary that it must be solid like salt or sugar. So what is solute and what is solvent in solution, as there are two parts? How to understand which one is solute and which one is solvent? Because they may exist in all the states, right? So when we are talking about solvent, it is that component of the solution which basically dissolves the other component, and the main important criteria is it will remain in larger portion, that is the larger component of the solution, that will be known as solvent, and it has same physical state as the solution. Now this line is very important. Suppose solvent is water and solution that is also liquid. So solvent is liquid, solution is also liquid. This must be same. But suppose if these two are contradictory to each other, suppose it is present in larger amount. Suppose in 100 gram solution there is 60 gram of sugar and 40 gram of 60 gram sugar and 40 gram water. So as we have said that it is the larger component. So according to the definition, sugar must be now solvent and water must be solute. But actually that is not the case. Why? Because here the second point is important. Though these two are here contradictory, but this point is important. Because after mixing these two, the final solution that we will get, that is actually liquid. So the state, that is physical state of the solution is liquid, and physical state of which component is liquid? It is the water component, because sugar is solid. So though sugar is present in larger amount, but still sugar, we cannot call it here solvent. Sugar is still solute. So the second point is very important, that solvent must have the same physical state as that of solution. So if solution is liquid state, that is the physical state of the solution, if it is liquid, then the physical state of the solvent, that also must be liquid. As in case of sugar, though it is present in larger amount, but still this condition is not fulfilled. So that is why we cannot call sugar here solvent. Here water is the solvent. And what is solute? Obviously if it is present in larger component, solute will be present in it is smaller component, not larger. Okay, so it will present in lesser amount, and the component of the solution which dissolve in other component, that means solute is dissolved in solvent. Okay, so this is the difference between solvent and solute. Expressing concentration of the solution. So first of all we have to know what we mean by concentration. So when there is a solution given, the amount of solute that is dissolved in a unit volume of solution or unit amount of solvent. So both may be possible, because concentration can be expressed in different way. So that is why it may be unit volume of solution, sometimes it may be unit mass of solution, or unit amount of any mass or volume, whatever it is. It may be for solution as well as for solvent. So this is known as concentration of the solute. Okay, so solution containing relatively high concentration of solute, that is when the amount of solute per unit amount of solution or solvent is very high, we will call this solution as concentrated, and if it is relatively low, we will call it dilute solution. But if we have two solutions and we are saying the first solution is concentrated, the second one is dilute, we can have some idea, but we cannot exactly say what is the amount present. That is, it is a just qualitative idea, it is not quantitative idea. Unless we know the exact amount, the quantitative idea we cannot get. Okay, because these terms are actually relative terms. Actually, what is the exact condition for concentrated solution? There is no such definition. We simply say that when the amount of solute is very high, it is concentrated. But how to know that whether it is high amount of solute that is present in solution? For that we have to know the exact figure of the concentration. Fine. Now for this expression, there are several ways by which we can describe the concentration of the solution quantitatively. Okay, so one by one we will see each of them. The first one is mass percentage. So in mass percentage, how we will define it? It is the amount of solid in gram present in 100 gram of solution. Be very careful about this solution, whether it is solution or solvent, that is very important. When you will solve numerical problems, if there is any doubt in this line, that is 100 gram of solution, you will make mistake, because 100 gram of solution and 100 gram of solvent both are not same thing. So the definition must be very clear. It is the amount of solute in gram present in 100 gram of the solution, not solvent, it is solution. So mass percentage, how we can calculate it? It is mass of solute divided by mass of solution. All are in gram because it is mass. That is why we have written here W by W. That means both are weight here, and multiplied by 100, and by mass of solution, basically it is mass of solute as well as mass of solvent, because solution has two parts, one is solute, another one is solvent. So that is why by mass of solution, what we mean? We mean the mass of solute as well as the mass of solvent. Okay. So one example we have here, 10% solution of sugar by mass, that is by weight. So what we understand by this fact? It means that 10 gram of sugar is present in 100 gram of solution. That means what is the amount of water? It will be 100 minus 10, because this is the mass of solution, this is the mass of solute. So if we subtract the mass of solute from mass of solution, we will get the mass of solvent. So 90 gram of water is present. Okay, so these are very important to understand, because to solve numerical problems, we should have proper clear idea about the formulas and definitions of these different types of concentration terms. So this is the first type by which we can describe the concentration of solution quantitatively. Both are mass of solute, mass of solution. The next type is volume percentage. So when it is volume percentage, that means it is V by V. Sometimes you will see numericals, it is simply written V by V. That means volume percentage. It is defined as the volume of solute in ml present in 100 ml. So it is just like the previous one, only difference is now in place of mass we have volume, unit is ml, and here instead of 100 gram now we will have 100 ml solution. So the volume percentage will be volume of solute divided by volume of solution. So when we say 10% solution of HCl, what we understand? We understand that 10 ml of liquid HCl that is present in 100 ml of the solution. Okay, so 10% solution V by V. If we say here, this also must be mentioned, it is V by V, volume percentage. So 10 ml of HCl, 100 ml of solution. That means the amount of solvent, that is water, will be 100 ml minus 10 ml, that is 90 ml. Fine. The third one, mass by volume percentage. Now we have combined mass, volume together, and mass is for solute and volume is for solvent. Solution. So it is defined as the mass of solute, mostly it is present in gram, in 100 ml solution. Okay, so this is W by V. So mass of solute divided by volume of solution. Now if we say 10% mass by volume, or sometimes it may be written as W by V also, solution of NaCl, what we understand? We understand that 10 gram NaCl is present in 100 ml of solution. That means the amount of solvent here you directly cannot get, because this is in gram unit, this is in ml unit. So we cannot simply deduct this 10 from 100. Okay, we have to know the density of the solution also. Otherwise we cannot directly get the amount of solvent. Okay, so this is the mass by volume percentage, W by V. Now we have a problem which is related to mass percentage formula. Okay, 40% by mass of urea obtained when 190 gram of urea is dissolved in 400 ml of water. Fine. So here mass percentage concentration is given, that is 40%. 40% W by W, that is given. Another information is given, that is the mass of urea, and the volume of water, that is also given, which is 400 ml. So we have to find the density of the solution. So if we apply this formula, here mass percentage is given, so we can write here 40, which is equal to mass of solute. Now mass of solute is given, which is 190. Okay, and mass of solution, that we do not know. So suppose the mass of solution is W multiplied by 100. So from this equation we can get what is the mass of solution. So mass of solution, it will be 190 divided by 40 into 100, and that is equal to 475 gram. So this is the weight of solvent. Okay, sorry, it is weight of solution. Mass of solution, not solvent. So mass of solution is 47 gram. Now volume of solvent is given. Volume of solvent, in this case solvent is water, which is 400 ml. Okay, so if it is 400 ml, and here we have to consider one fact, which is we will assume here that volume of solvent is equal to volume of solution, because we have to find density of the solution. So for that we know that density is mass by volume. So here we know the mass of solution, which is 475 gram, but we do not know what is the volume of the solution. Okay, but we know the volume of solvent. So when we will add 190 gram urea to this 400 ml of water, there the volume change will be there, but it is so insignificant that we can assume that volume of solvent and volume of solution both are same. So if it is same, now we can write 475 divided by 400, and that is equal to 1.19. What will be the unit? It will be gram per ml, because this is in gram, this is in ml. So in this way we can find the density. Okay, so in this way we can solve the problem. Next problem is 12.8 centimeter cube of benzene, that means cubic centimeter. This is the volume of benzene that is given, and 16.8 centimeter cube of xylene. So this is also the volume of xylene, that is also given. Both are liquid, benzene is liquid, xylene is liquid. Calculate percentage by volume of benzene. So this formula we have to use here, because it is volume by volume. So which one will be solute and which one will be solvent? How to understand that? Just look at the amount. So the larger component must be solvent and the smaller component must be solute. And also see here the final physical state of the solution is liquid, and both are in liquid. So simply we have to see that what is the larger component. So this is the larger component. So that is why here xylene is solvent, benzene is solute. Okay, so volume of solution, how to find out that? So volume of solution is simply add the volume of solvent and volume of solute. Volume of, I have taken quite common, solute, solvent. So solute volume is 12.8, solvent volume is 16.8. So it will be 29.6 centimeter cube. Okay, so now we know the volume of solution, so we can put it in the denominator, and we already know what is the volume of solute because this is directly given. So volume percentage, that is calculate percentage by volume of benzene, because benzene is the solute, it will be 12.8, which is the volume of solute, divided by 29.6. So this will be 43.24%. This is the answer. Calculate the percentage by volume, that is V by V. This is V by V. So 3 we have seen. This is the number 4 type of concentration by which we can express it. So what are the 3? Mass by mass, mass by volume, and mass by volume. So these 3 we have already seen, and this is the number 4, which is molarity. So molarity, how we will define it? It is the number of moles of solute which is dissolved in 1 liter, or you can say 1 cubic decimeter. Okay, dm3. That in that way also it can be expressed. Sometimes in numerical you will find that in 1 liter you can also say 1000 ml or 1000 cc. Okay, so number of moles of solute present in 1 liter of solution. Be very careful, it is solution, it is not solvent. Okay, so molarity, how we will calculate it? Number of moles of solute and volume of the solution, which must be in liter. Okay, that is per liter. What is the number of moles? That is actually the molarity. So here we have one example. Suppose we have 2 molar solution of KCl. So what we will understand by this, it means that 2 moles of KCl, that is the solute, this is solute, that is dissolved in 1 liter of liquid. So unit of molarity, it must be moles per liter, because numerator is moles, denominator is liter, so it must be moles per liter. And see, in this formula we have volume involved. Now volume, as it depends on temperature, that means molarity will also be dependent on temperature. Though most of the time in numerical or in books you will see that whenever molarity is mentioned, temperature is not mentioned, right? So by default you can consider that it is at room temperature, that is under normal condition. But it is, if it is very drastic condition, suppose very low temperature or very high temperature, which is very rare cases, then molarity, obviously it will change because volume will change. So molarity has to change. Okay. Now numericals, you will find that sometimes instead of molarity some other terms are involved. For example, it may be mentioned as 0.5 molar or m by 2. That actually means semimolar. So it can be written like semimolar solution of KCl. So that means 0.5 molar solution of KCl. If it is mentioned decimolar solution of KCl, that means m by 10 molar of KCl. So deci is 1/10 of molarity and semi is half of molarity. Similarly, if it is centi, it is 1/100th of molarity, that is 0.01, and if it is millimolar, it will be m by 1000, that means 0.001. So we have to read the numericals very carefully, whether it is semimolar mentioned or decimolar mentioned or simply molar solution is mentioned. So if it is written that molar solution, it simply means molarity is 1. If it is semimolar, molarity is 0.5. So in this way we have to consider, here all these terms are mentioned. Okay. Now we will solve one problem which is related to molarity. So in this question you can see decimolar is mentioned. Okay, so as decimolar is mentioned, that means which one we will consider? It should be m by 10. Decimolar solution means the molarity is 0.1. Okay, so first of all we will write that here molarity is 0.1 or 1 by 10, and we have to find quantity of anhydrous sodium carbonate which will be required to produce 250 ml of 0.1 molar solution or decimolar solution, whatever, both are actually same thing. But for that we have to find out the molar mass of sodium carbonate. Now it is mentioned anhydrous sodium carbonate. Why it is mentioned? Because Na2CO3, there sometimes what happens, some water molecules or crystallizations are attached to it, suppose XH2. So when that water of crystallization is attached, then when you will calculate the molar mass, you also have to consider the weight of water molecules. But here it is simply clearly mentioned that anhydrous sodium carbonate, that means there is no water molecules attached. So simply from this formula we will find out the molar mass of sodium carbonate. Molar mass of Na2CO3. So for 2 sodium it will be 2 into 23, for carbon 12, for oxygen 3 into 16. So this will be 106 gram. Okay, now here the final concentration is given, which is 0.1 mole. Now according to the definition of molarity, this number of moles actually present in 1000 ml solution. According to the definition, so we can say that 1000 ml solution contains 0.1 moles sodium carbonate. That means, but we don't require 1000 ml, we just need what will be the number of moles in 250, because that amount we have to find out. So 250 ml will contain how many moles? It is 0.1 divided by 1000 multiplied by 250. Now this is 4. So 0.1 by 4, it will be 0.025 moles. Now we know what is the number of moles of Na2CO3 present in 250 ml, and we have to just convert it to weight, because we know the molecular weight. This is the molecular weight. So number of moles is basically given weight divided by molar mass. So here we basically will find out the given weight. So what we will do, we will simply multiply the molar mass, which is 106, with the number of moles, which is 0.025. So the quantity of anhydrous sodium carbonate that is required, that weight will be number of moles 0.025 multiplied by 106. So it will be 2.65 gram. Okay, so this is the quantity of anhydrous sodium carbonate where no water molecules of crystallization present will be required to prepare 250 ml decimolar or 0.1 molar solution. Okay, another problem. So here we have two things combined. One is 40% HCl gas by mass. So this is one way by which we can express the concentration. And another thing is also mentioned, which is calculate molarity of HCl solution, which is another way of expressing the concentration. So sometimes in numerical these are very common, that is concentration in one type will be given and we have to find the concentration in another type. Suppose molarity is given, we have to find out the mass by mass, or mass by mass is given, we have to find out mass by volume, etc. like this. So we have here commercially available concentrated HCl. So this concentrated HCl, its concentration is given as 40% HCl gas by mass. That means here weight of HCl will be 40 and the mass of solution will be 100 gram. So 40 gram HCl in 100 gram solution. This is the meaning of this line. So if that is the case, then what will be the mass of solvent? Simply we have to deduct 40 from 100. So mass of solvent will be 100 gram minus 40 gram, which is equal to 60 gram. Okay, so now we know what is the mass of solvent, and here density is given and 40% HCl gas by mass. These two information is given. From these two information we have to find molarity. Now molar mass of HCl, sometimes it may be given in the question, sometimes it may not be given, then you have to calculate it. It will be 1 for hydrogen and 35.5 for chlorine. So it is 36.5 gram. Okay, now 40 gram HCl is present. So what is the number of moles? Number of moles of HCl is given mass, that is 40 gram, divided by molecular weight, which is 36.5. So that is why we have calculated the molar mass, because to find out the number of moles of HCl we need the molar mass of HCl. This is 1.096 moles. Now here density is given. So what is the meaning of this? 1.2 gram per centimeter cube. That means 1 cc or 1 ml has weight 1.2 gram. Density is given 1.2 gram per centimeter cube. So it means 1.2 gram is the weight of 1 cc solution, or you can say 1 ml, both are same. So 1.2 gram, if it is the weight of 1 cc solution or 1 ml solution, then if we can find out what is the volume of 100 gram solution. This is basically 1.2 gram solution, 100 gram solution. It will be 1 by 1.2 multiplied by 100, and this is 83.33 ml. So now we know that 100 gram solution, what is the corresponding volume? So this is the volume of solution. So why we have calculated volume of solution? Because we have to calculate ultimately the molarity, and to calculate molarity we need the volume of solution. Okay, so in this volume of solution, how many moles of HCl present? It is 1.096, which we have already calculated. Okay, so we can write now that 83.33 ml solution contains 1.096 moles. Now what is the definition of molarity? The number of moles present in 1000 ml of solution. So 1000 ml will contain 1.096 divided by 83.33 multiplied by 1000. So it will be, so this is the molarity. This is very high value because this is concentrated HCl solution, that is why it is very high value. Okay, so in this way we can find out from mass by mass percentage and density. From these two information we have ultimately calculated what is the molarity of HCl solution. Another question regarding molarity, because molarity, then we will also see after this molality. These are the mostly used concentration terms. Mass by mass, mass by volume, these are to some extent it is also, they are also used, but to some extent it is less. So you can find that numericals related to molarity and also molality, which we have not discussed yet. So based on these two, numericals are mostly there. Okay. So here we have two solutions of a substance. Two solution of a substance, and the substance is non-electrolyte. That means it is not dissociated into any ions. Okay. They are mixed in the manner. One solution is 480 ml and the corresponding molarity is given. Suppose it is solution 1. Another solution, volume is 520 ml and molarity is also given 1.2. So basically here mass and concentration, these two values are given. So for solution 1, we will consider this is as M1 and the volume is V1, and suppose this is V2 and this is M2. Now we have to find the molarity of the final solution. That is, when we have added this 480 ml of 1.5 molar solution, which is solution 1, it is added to solution 2. Okay. So suppose the molarity of final solution is M and final volume is V. So V is equal to 480 plus 520. Very simple. Now the formula that we will use here, whenever you will get this type of problem where the same solute has two different solution having two different concentration. So the first solution is 1.5 molar, second solution is 1.2 molar, but here solute is same. Okay, so whenever this type of problem is given, we can use this formula, that is M into V, that is the molarity or concentration of the final solution. This is the volume of final solution, and that is equal to M1 V1 plus M2 V2. So 480 plus 520, we have to add these two volume, and M1 is 1.5, this is V1, this is M2, this is V2. So after calculation we will get the molarity of final solution, which is 1.344. So it is matching with option C. Here 4 options are given, it is matching with option C. Okay. Now the fifth one, that is molality. After molarity it is molality, and though these two terms are very close, only in place of R now we have L. So be very careful whenever you are reading the numericals, because if you miss this L or R, your calculation will be there will be error. Okay. So what is the difference of molality and molarity? In the previous case we have seen it is the number of moles in 1 liter of solution, but now there are two different things. Now it is 1 kg and now it is not solution, it is solvent. So two things are different. Now it is 1000 gram or 1 kg and it is not solution, it is solvent. So molality will be number of moles of solute divided by mass of solvent in kg. Okay. Now this is the most convenient method to express the concentration. Why? Because it does not involve the volume. It is simply involving the mass of liquids rather than their volume. Okay. So it is, that means it is independent of variation in temperature. So if temperature, there is fluctuation of temperature, that means there will be no change in the value of molality. But if it is molarity, there will be change. But as it is molality, there is no volume involved. It is only the moles and mass of solvent. So there will be no change with variation in temperature. So that is why it is a very convenient method if we compare with other methods. Okay. Now next one is normality. This is also equally important, and it is defined as the number of gram equivalent of the solute present in 1 liter of the solution. So it is also, you can find some similarity with molarity, because in molarity also it is 1 liter solution. So this part is actually common with molarity. But what is the difference? In case of molarity, it is the number of moles of solute, but now it is gram equivalent. Okay. So normality will be number of gram equivalent instead of moles. and this denominator part, that is same. It is just like molarity. Only difference is in the numerator, that is the number of gram equivalent of the solute. Now how to find this number of gram equivalent? It is very easy. Number of gram equivalent of solute, this is actually the mass of solute in gram and the equivalent weight of solute. So when we calculate number of moles, what we do? Given mass, that is mass of solute divided by molar mass. But now instead of molar mass, what we are taking? Now we are taking equivalent weight. Now equivalent weight, how to find that? That can be found, but for that you have to know the valence factor. It is also sometimes written as N factor. So molar mass of the solute, it will be divided by valence factor. Now in numericals mostly you will find acid or base. Elements also may be there, but it will be less. Mostly it will be base or acid. And valence factor for base, it is very easy to calculate. It is simply the acidity of base and basicity of the acid. So suppose if it is H2SO4, then what will be the valence factor? Then the valence factor will be 2. Valence factor will be 2. Why? Because when 1 mole of H2SO4 is dissociating, basically we are getting 2H plus. But suppose if it is HCl, what will be the valence factor? Valence factor will be 1, because from 1 mole of HCl we are getting 1 mole of H plus. Okay. So if we want to find out the equivalent weight of H2SO4, what we will do? We will first calculate the molar mass of H2SO4, then we will divide it by 2. So it will be lesser than the value of molar mass. Now once we get the equivalent weight of solute, now the given mass, that is the given mass of solute, if we divide it by equivalent weight, we can find out the number of gram equivalent of the solute. And if it is element, any other element, then it will be the valence. So suppose if I say copper, mostly it is copper 2 plus. So you have to first see that what is the oxidation state of the element which is present in the compound. Accordingly, the valence factor will change. Okay. So in case of normality, we have to do some extra calculation, because we have to find gram equivalent. It is not directly you put the molar mass and you will get the gram equivalent. It is not like that. For calculation of gram equivalent, we have to know what is the equivalent weight. And to know the equivalent weight, we have to know the valence factor. Okay. Now, just like molarity, the same thing we have already seen, right? So, if we are saying that normal solution of something, it will simply mean that it is 1 normal. Okay. If we are saying that semi-normal, it will be n by 2. So, same thing we have already seen in case of molarity, that is semi-molar, decimolar, centimolar. Now we have semi-normal, decinormal, that means 0.5 equivalent, because it is n by 2, 0.1 gram equivalent, because it is n by 10, 0.01 gram equivalent. Just see that it is simply the analog of whatever we have seen in case of molarity. In case of molarity, what we see? It is 0.01 moles, but now we are saying everything is same, only the difference is now it is gram equivalent. In short, we can also write it as G dot E equivalent B. Okay. So we have to be very careful whether it is mentioned, because if you are reading the question in a hurry, you may miss whether it is semi-normal or semi-molar. So be very careful. Okay. Now we have a problem which is related to normality of acid. Calculate the normality of acid. So what information is given? 21.18 ml of it is used to titrate 0.1369 gram of Na2CO3. That means here the acid, which acid that is not mentioned, that is not required also. This acid is used to titrate this amount of Na2CO3. That means whatever will be the equivalent, gram equivalent of Na2CO3, it will be same as the gram equivalent of the acid. Okay. Now here weight is given, and we can easily calculate the molecular weight of Na2CO3. So from that we can find out what is the number of moles of this Na2CO3. And once we know the number of moles from the valence factor, we can also find out what is the gram equivalent. Okay. So first of all, we have to find out what is the molar mass of Na2CO3. We have just done it some in other problem, but again I am doing this. 2 into 23 for 2 sodium atom, 12 for 1 carbon atom, and 3 into 16 for 3 oxygen atom. This will be 106 grams. So this is the molar mass of Na2CO3. Now gram equivalent you can find out by two methods. Whichever you find better, you can follow that. So I am showing here both this. Suppose this is method 1 and this is method 2. From both method we will get the same answer. So in case of the first method, the gram equivalent, how to find out that? So here number of, first we will find out the moles of Na2CO3 that is present in this weight, that is 0.1369. So 0.1369 divided by its molar mass, and that will be equal to 1.29 multiplied by 10 to the power minus 3. Okay, so gram equivalent of this, if we want to find out, gram equivalent will be number of moles. Remember, we have to multiply it with valence factor that we have seen in the previous slide, that is equivalent weight equal to molar mass divided by valence factor. So 1.29 into 10 to the power minus 3. So what is the valence factor of Na2CO3? It will be 2, because from Na2CO3 we can get 2 Na plus. Okay, so this is a base, so acidity is 2, so it will be divided by, it will be what we have seen here. It is equivalent weight, which is molar mass of the solute divided by valence factor. Okay, so if that is the case, so here I have done one mistake. It is basically multiplied by n. So in the previous slide what we have seen, it is the equivalent weight of solute. When we will find out, then it is molar mass of the solute divided by valence factor, but we are not doing that. We are not calculating equivalent weight, we are finding out the gram equivalent. So it will be simply the number of moles multiplied by, number of moles multiplied by valence factor. Okay, so valence factor is 2, valence factor. So I will, and if we do this, so remember it is number of moles multiplied by valence factor. So gram equivalent, it will be now doubled, so it will be 2.58 10 to the power minus 3. Okay, now this is method number 1. If we follow method 2, then we will reach the same answer, but here we will first find out what is the equivalent weight. So equivalent weight of Na2CO3 is, now we will apply this formula that we have used in the previous slide, that is the second line, equivalent weight of solute equal to molar mass of the solute by valence factor. So 106 by 2, so it will be 53. So this is the equivalent weight of Na2CO3. Now we will find out gram equivalent. So gram equivalent, just as we have calculated here, now it will be given weight, that is 1369 divided by 53. Okay, so now we will get the same result, 2.58 into 10 to the power minus 3. Fine. So we are getting same answer for gram equivalent. Whatever method you will find more comfortable, you can use that. Now once we know the gram equivalent of Na2CO3, so one equivalent of Na2CO3 is equal to 1 equivalent, because all equivalent weight of one substance always react with equivalent weight of other substance. Okay, so that is why we can write it 1 equivalent to CO3, 1 equivalent of acid. That means here 2.58 into 10 to the power minus 3 gram equivalent of acid will be present. Gram equivalent of acid. Now this amount, this gram equivalent of acid, that is present in 21.18 ml. But we have to find out normality. So we have to know what is the gram equivalent in 1000 ml of the solution. So now we can write 21.18 ml contains 2.58 into 10 to the power minus 3 gram equivalent of HCl. So 1000 ml will contain 2.58 10 to the power minus 3 divided by 21.18 multiplied by 1000, that is 10 to the power 3. So these two will be cancelled and we will get 0.122. So this is the normality. Okay. Next problem is regarding molality, and what information is given? Here density is given. Density of 5.35, this is not small m, this is actually capital M, because capital M is used for determination of, that is expressed for molarity, and small m is used for molality. Here answer is given 7.69. So density of 5.35 capital M, if it is mentioned, that means it is molarity, and if small m is mentioned, it is molality, but we have to find molality, so it must be capital. So density of 5.35 molar H2SO4 solution 1.22 gram per centimeter cube. So basically we have two informations given, one is density given, another one is molarity given. So from these two information we have to find out molality. Okay. Now as density is given, so we can write from this information that 1 cc or centimeter cube or ml, whatever we say, it has weight 1.22 gram. So 1000 ml should have weight 1220 gram. Very simple. Okay. Now we will find out what is the weight of solvent, because for calculation of molality it is the weight of solvent which is required, not weight of solution. So this is the weight of solution. This is weight of solution. Okay. But to find out the weight of solvent, first we should know what is the weight of solute. So if we subtract the weight of solute from weight of solution, we will get weight of solvent. So how to find out the weight of solute? Because solute is here H2SO4, this is solute. So we should know what is the molar mass of H2SO4. If it is not given, we have to calculate it. So 2 into 1 for hydrogen, 32 for sulfur, 16 into 4 for oxygen, and this is equal to 98. So 5.3 moles, that is present in this amount of solvent. So now we know the molecular weight, we also know the number of moles of H2SO4 that is present in 1 to 2 gram of solution. So weight of H2SO4 will be weight of H2SO4, that means weight of solute, that will be 98 multiplied by the number of moles 5.35, and that is equal to 524.3 gram. So now we know the weight of solute, we also know the weight of solution, so we can find out weight of solvent by subtracting 524 from 1220. This is 695.7 gram. Okay, so this gram of solvent, it is actually carrying this number of moles of H2SO4. Fine. So we can now write 695.7 gram of solvent. This amount of solvent, there is presence of 5.35 moles of solute, moles of H2SO4, which is solute here. So 1000 gram, that means 1 kg will contain how many moles? That is actually we have to find out. And this will be equal to 7.69. The answer is given in the question already. Okay, so from density and molarity, from these two informations, we have calculated the molality of the solution, which is 7.69. So here the molarity is 5.35 and molality is higher than that. There is no hard and fast rule whether it will be higher or lower, and that depends on the density. If density is very high, that means this value will also be very high. That is the value of molality. Here we have another problem. Let me erase it. This problem is actually very simple. So here we have a reaction given, and from this reaction, that is the equation basically, we have to find the normality when it is given that 1 molar H3PO3, that is H3PO3, that is the, sorry, it will be H3ASO4, that is a mistake. It is H3ASO4. Actually phosphorus and arsenic both are from same group, so that is why I have made the mistake. By mistake I have written phosphorus in place of arsenic. So H3ASO4, it is reacting with NaOH. So this is basically acid. Okay, it is reacting with NaOH, but here what is the basicity of acid? 3, because 3 replaceable hydrogen is present, but only we are using 2 NaOH. That means out of 3 hydrogen, only 2 hydrogen replaced by sodium. Okay, so from this equation we can understand what should be the valence factor. Out of 3, only 2 hydrogen is replaced. If all the 3 hydrogens are replaced, valence factor will be 3. But here from the equation it is clear that we have to understand, because directly the valence factor is not given. From the equation we have to understand what is the valence factor. So once we know the valence factor and molarity is already given, we can easily calculate the normality. Okay, so here only 2 H plus ions of H3SO4 acid is reacting with NaOH to form the product. So 2 ions are basically 2 equivalent. So number of equivalent or valence factor, whatever we say, this is actually same thing. We have to multiply it with molarity, and ultimately we will get 2.0. So this is the normality of the solution. Okay, so this is another completely different type of problem, which is very simple. Once you understood the basic fact, it will not take much time. Okay, so read the question very carefully. See how many hydrogens are replaced when this type of multi basicity acid or multi acidity base is given. We have to be very careful. Okay, formality, this is the number 4. Until now we have seen already 6. This is the number, sorry, it is number 7. So what is formality? Now see, formality is very rarely used, only in some cases it is used. Okay, but still we should know what is formality, because you may get numerical problem regarding this. So it is the number of formula mass in grams present per liter of the solution. So per liter of the solution, this part is just like normality and molarity, same as normality and molarity. But what is the difference? Now we have to find the formula mass, number of formula mass in grams. Okay, so what is formula mass? So in case of formula mass, we will come to that point. First see, if the formula mass is same as molecular mass, then formality and molarity both will be same. And just like molarity and normality, formality is also dependent on temperature, because here volume is involved. Okay, so in case of molarity, what we have seen, number of moles of solute, right, divided by volume of solution. So this part is common, volume of solution in liter. But now instead of moles of solute, we have this figure. So weight of solute, that is the given mass, divided by formula weight of the solute. Okay, so this is the number of formula mass. That is, number of formula mass means what? Given mass divided by formula weight of the solute. Okay, so when this type of concentration terms are used, basically it is used in some cases where formula mass and molecular mass, these two are not same. In most of the cases it is same, but in some cases it may not be same, because some molecules may exist as dimer. Okay, so a very good example is acetic acid. We will also solve a problem regarding this. So acetic acid, if we simply calculate the molar mass from this molecular formula CH3COOH, then you will get molar mass, but actually it remains in dimeric form. That means the formula mass will be different from molecular mass. So the problem is CH3COOH, acetic acid, exists as dimer in benzene, not in all solvent, it is in benzene. So we have 1.2 gram of the acid which is dissolved, and the volume was made up to 1 liter. That means the volume of the solution, that is directly given 1 liter, because after adding the acid, because acid is also dilute, so after dissolving it, volume was made up to 1 liter. That means it is after addition of the solute, the final volume of the solution is 1 liter. So this is basically volume of solution. So if this is the volume of solution and CH3COOH, it exists as dimer. Now if it is existing in dimer, then first of all molecular weight we will find out. So molecular weight of CH3COOH is 2 carbon, so 12 into 2, 4 hydrogen, 4 into 1, and 2 oxygen, 2 into 60. So this will be 60. Okay, so if it is 60, now we will find out the formula weight. So what is the formula weight? Because formula weight is basically we have to find out the weight of CH3COOH whole 2. That means it will be 60 into 2, 120. Now next we have to find out the formality. We will use this equation. So formality will be given mass in gram, which is 1.2, divided by 1.120, which is the formula weight. So this value is basically this portion, okay, multiplied by, this is actually divided by, but ultimately the equation will be like this. So this is already given 1 liter. So finally the formality will be 0.01, and it is expressed by F. Okay, just like molarity we expressed with capital M, molality we expressed with small m, this will be expressed in capital F. Okay.